This video is on lesson 3.3, and we're going to talk about equations of a line in three-dimensional space. So we had talked about lines in two-dimensional space before, and several different types of equations kind of popped up. Okay, let's go over those ones first before we move on. So in two-dimensional space, you had vector equations, and vector equations are made up of your position vector, x naught, y naught, plus a parameter, t, which is a scalar that's going to then multiply a, b, and that's your direction vector, or in other words, your slope. So another way of thinking about this is you're starting off at a point, and then you're going to add a certain multiple of your slope and get to a new position or a new point. You can write it like this as well, and it gives rise to the next type of equations, which is your parametric equations. So this x right here is going to equal to x naught plus t times the x component of your direction vector. So that'll give you this equation, and obviously you can do the same thing for your y and get another equation for your y component. In each of the equations, make sure that you put t belongs to all real numbers at the end, because we're just saying that the scalar that is multiplying your direction vector has to be a real number. The third equation is your scalar Cartesian equation, and that is the only one out of the three, I should say, that shows you what your normal is. And so the normal vector in this case is your a, b, and that's a perpendicular vector to your line. So if I decide to play with some of these equations a little bit, I'm just going to start to play with the parametric equation, and I end up with a fourth one called the symmetric equation. And you're just like, why? Why would you do that to me? I don't know, because I felt like it. It's not me. I didn't actually come up with these. So it's not personal. Okay, so x minus xo. I'm going to just solve for t here. Divide by a, and I get t is equal to the x value of your new point minus the x value of your old point over the x value of your direction vector. Okay, and if I do the same thing over here just really quick, I should get something like this. You'll notice that both equations equal to t, and so we can rewrite it like this, where they're equal to each other through substitution. And notice that a and b obviously can't equal to 0 because your denominator should not be 0. But this gives rise to your last ones, which are called your symmetric equations. Since we have all four, any of the questions could say, I want you to show me the answer in vector equation, or I want you to show me the answer in symmetric equation. So you kind of have to know how to work back and forth between each of them and just roll with the punches, guys. So these are what they look like in 3 dimensions now. Pretty much very logical. I mean, if you look at the vector equation, you have a third component for each of the vectors, right? For the parametric equation, as you would expect, you have a third equation, your z equation. Okay, now the Cartesian scalar equation doesn't actually exist. The reason for that is because in 2 dimensions you have a specific normal vector, but in 3 dimensions you have way too many. There isn't a unique one, you have infinite of them. And so it's very difficult to find one Cartesian or scalar equation. The only way that I can think of right now to explain it is, here's your line, and imagine it as the trunk of a Christmas tree. I don't know why I'm thinking about this. Maybe it's because there's snow outside or something like that. It's winter. What you can think about is a normal vector could be like the branches, and there are infinite number of branches in 3 dimensions that would then be perpendicular to your tree, and so there just isn't a unique equation to describe that line. Again, I have no idea. Maybe I want it to be Christmas again. Get myself a nice break. Actually, March break is coming up, except I'm probably going to be here making videos. All right, last one. Symmetric equations. You have a new fraction at the end, and that sums up all of the equations in 3D. So let's start tackling some of these questions. The first question says, is the point -2, 9, -2 on line 1? Okay, so they've given you line 1, and line 1 is in parametric form. Okay, so intuitively, I think a lot of times what we would do is we would just start labeling this and subbing it in wherever we could. Okay, and that's not wrong actually. You're going to take your x, which is -2, and you're going to put it into the x for your parametric equation. I made it equal to 6 plus 4t, and this one would be your y component is equal to 5 minus 2t, and then your z component is equal to 4 plus 3t. Now that you've subbed in each of your components, you can then solve for t. Okay, bringing 6 to the other side, you get -8. Dividing both sides by 4, you get -2. And what you're looking for is that all of your parameters are actually the same. If your parameters are consistent, it actually means that this point exists on line 1. If your parameters are different, even if one is different, like 2 of them can be the same and one of them can be different, it doesn't matter. They have to all be consistent, and that's how you would know that that point is on the line, like it's lying on the line, instead of just like floating around the line. Okay, so let's try out some more examples. I think I have about 5. Example number 2, find the vector and parametric equations for a line passing through 2 points. In grade 9, we had talked about find the equation of a line passing through 2 points. And the first thing you would do is you would find the slope with those 2 coordinates. Except I have no idea how to find the slope of 3-dimensional vectors, but I do know how to find the direction vector, which is kind of like a slope. We have our A in blue, and then we have our B in pink. Okay, so we're going to find a direction vector, and it doesn't matter if you do A to B or you do B to A. I'm going to show you why in a second. I just chose A to B, and so you take OB minus OA and subtract them. You guys should know this. And you get your direction vector. Now, I would simplify that by taking out a common factor, which is -1, and just have your simplified direction vector that you would then put behind your parameter. Okay, now what I was saying is that it really doesn't matter if this is AB or BA, because this number right here that comes out as a scalar amount, it's like junk. I don't really need it. And so all I need is the 1, 2, 2, which I put into here. That -1 is then disappeared. Is not good English. Has then disappeared. It's been absorbed into the parameter. And so no matter what that scalar is, it's just going to be hidden within t. So it really doesn't matter what it is. To complete the vector equation, you need a position vector. And so whether you choose A or you choose B, just like in grade 9, when they're like, you choose A or B and you sub it back into your equation to find your, I think your equation or your y-intercept. It really doesn't matter if you use A or B, and so I just said, I'm just going to use A. Now, could you also have an equation that uses B like this? Same direction vector. Yeah, absolutely. Okay, so both of those equations are actually correct for this question. You can have either on a test. However, if I actually want to put them into parametric equation, which they're asking for next, I might want to just choose one of them. I don't want to do both of them. Okay, so let's just choose the very first one. I'm going to move this down. I'm going to change this one to the parametric. So that's the one with the x, y, and z. Your x is over here, 4, plus the t times your x is 1t. Okay, for the y's, it's -5, right here, times 2t. Sorry, not times 2t, plus 2t. And then this is 3 plus 2t. And all of these have to say t belongs to all real numbers. So that is the parametric, which is the best form that I can use in order to see if a coordinate lies on that line. And so I'm going to use my x, y, and z and sub it into my x, y, and z in order to see if my t's are consistent. Okay, so t equals to 4 plus, not t, 2 equals to 4 plus t, I apologize. Negative 9 is going to be equal to my y formula, and then 1 is going to be equal to my z formula, and I start solving and solving, and it looks like, nope, t's are not consistent. They're not the same. They're not constant. Okay, so in that case, we can conclude C is not on this line. Okay, I need a little bit more space for this one, so I'm just going to make that jump. Example number 3. Find the vector and symmetric equations of a line that passes through a certain point. Okay, so they've given us that point, which I'll probably use later as a position vector. But my direction vector, it has to be perpendicular to two vectors. Now you had learned in the last unit, if I'm finding a vector that is perpendicular to two other vectors, I'm going to have to do the cross product. Okay, so you can see the cross product on the left-hand side. I'm not going to go through the cross product. That's going to give me my direction vector right over here, which I put after the parameter t, and I'm going to use my a as my position vector. Okay, so done and done. The symmetric equation. Okay, symmetric equation means that I should probably put it into the parametric equations first, and then I'll put it into the symmetric equation. It doesn't have to be in that particular order, it's just easier to see. And so parametrics look like this, where my x is 3 plus 4t, and then my y negative 1 plus 7t, and my z is 2 minus 1t. T belongs to all real numbers. Okay, so that's parametric. Putting it now into the symmetric means that I solve for t for each of those equations. So bring this to the other side, x minus 3, and then I'm going to divide it by 4 to get t by itself. Do the same thing to the other one. So bring this to the other side, divide by 7, and that's going to equal t as well. So let's just get rid of this and write that down because they're equivalent. Plus 1 over 7. Doing that to the z minus 2 divided by negative 1. Okay, and that is our equations in the symmetric form. So I know that I'm just going to address something because I know that some of you guys are going to want to do this. Don't put this negative back onto the top. I know in grade 9 we've drilled it into you guys, no negatives in the denominator, no negatives in the denominator, no negatives in the denominator. Okay, also no ones in the denominator. But it makes it easier for me to see this negative 1, as my component here. Like if I ever had to rewrite this into a vector form instead of a symmetric form, I could then easily see the negative 1 in my direction vector. Okay, so please make sure that your x, y, and z are always positive. And if they're not, try to rearrange things so that they are. I'll show you in this next one, which I have a box around for some reason. You know what? I'm just going to start writing and then it'll disappear. Okay, so equation number 4. Example number 4. I love saying equation for some reason. Given the following symmetric equations, find the point on L1 that corresponds to a parameter of 3. And so this is a parameter of 3, and this box is not disappearing. So let's just click. There we go. So the parameter is 3. They're telling me t is 3. And what I want to do is I want to find an x, y, and z point that lies on that line if that parameter is 3. So what I'm going to do is I'm going to take my equation, which I've been given in symmetric form, okay, and I'm going to start solving. This guy is equal to t, which I have the equation right here. This guy is also equal to t, so t is equal to 1 minus y over 2. And this guy is also equal to t, plus 9. Okay, so since I know that t is 3, I can easily just solve each of the equations where 3 is on the left-hand side. And I get an x, y, and z, which then make up that point that they were looking for, -5 and 6. Now, another way that you could do this, although I think I'm partial to the left-hand side, is the right-hand side way. And so what I want to do is I want to show you on a separate slide, because remember how I said that I never want a negative in front of the y? I'll show you what you should do. So I'm going to have the exact same slide, okay? And what I want to do is I just want to change it to vector form. Now that they're in symmetric form, why don't we first change it? Actually, I'll write it out like this. This equals to t. This equals to t as well. And we know that there's a 1 underneath. So let's write that as well, equals to t. Okay? Just trust me. I'm going to show you something. Start solving for x. Bring 4 to the other side first. X minus 5 equals 4t. Same with this guy. And this guy. Okay, and then bring each of those numbers to the other side so that your components are by themselves. +5 plus 4t. This one's going to be a little bit confusing. See what I mean? Like, it gets a little bit confusing when there's a negative in front of the letter. But anyways, -1 plus 2t. And then we have z equals to -9 plus t. Okay, and I'm just going to fix this one up. 1 minus 2t. Okay, once it's in this form, I can easily see the x, y, and z is equal to these guys, which are my position vector, 5, 1, and -9, plus my parameter multiplied by each of the numbers that is multiplying my parameter. So 4, -2, and 1. Okay, and remember, t belongs to all real numbers. What I did was I just changed it from symmetric form back into vector form. And you know what? You don't have to go through all these steps every single time. You'll start to see that you can jump from here down to here very quickly, because what you're doing is you're taking these numbers that are beside your positive components and you're doing the opposite of them. See, instead of this +9, now you write it as a -9. Except this one is not fun, this guy right here. I'm going to rewrite it. Why don't I multiply the top by -1 and multiply the bottom by -1, and I should get a -1 plus y over -2, which I like instead because it has the positive y, and I don't care that the bottom is a -2, because now I can see that opposite number is right here. Okay, and the bottoms are going to be my direction vector. Okay, so this guy is really important. Making sure that anytime you see a negative like component letter, so negative variable like -y, change it and just put a negative in the bottom instead. Okay, multiply the top and bottom by -1, and then the negative will kind of go into the bottom, the denominator, and you'll get your positive y instead, so that you can clearly see your position and your direction vectors. So using this equation, I was able to change this guy to this form instead, and then put my parameter, which was 3, in. I started to multiply and expand. Then I started to add my components together, and I get a new point, and that's the point that has a parameter 3 for line 1. Lastly, for each of the following, determine whether or not they describe the same line. So we have two lines, and when they say tell me whether or not they're the same line. They mean, are they coincident? And when I say coincident, I mean, are they not only parallel to each other, but does one point exist on another line? One point from one line exist on another line. Okay, so the first thing I'm going to do is I'm actually just going to write line 2 in a different form because it looks a little bit weird. It has like several things going on, and you know what, I'm just going to write it as x, y, and z is equal to, let's bring this to the other side of the equation and we'll get like a 4. Let's bring this to the other side of the equation, we get 4 again, and this guy as well to the other side, so we're just bringing those all over there. Plus our parameter, which is s, followed by our direction vector. Okay, and s belongs to all real numbers. All right, okay, now I can see it is a lot clearer. It's in vector form. I don't know what it was in before. It was just trying to trick us. We also have our other line. Okay, so the direction vector, which I just underlined, and this one's direction vector right here, we want to compare them and see if they're actually scalar multiples, because if they're scalar multiples to each other, that means that they're parallel. And it looks like, yeah, they kind of are, because if I just take this entire thing and I multiply it by -2, it looks like it actually becomes this one. Or in other words, if I take the orange and I divide it by -2, then I'll get the top one. So that means that they're scalar multiples. I can write them just like this, and they're parallel. Okay, so we know that they're parallel. Now to see if they're just separate parallel lines versus like on top of each other, why don't we see if this coordinate or position vector exists on this line? Because if it does, then that means they must be touching each other, which means that they're not separate parallel lines. Okay, so what I'm going to do is I'm going to check that that point is on line 2, and I'm going to sub in 1 right here, 6, and 2 into the equation line 2. And I'm going to check their parameters, and it looks like all the parameters match, which means that the point is on line 2, and that means that both lines are coincident. Okay, so I'm going to leave off with just a comparison between lines in 2 dimensions and 3 dimensions, and wish you a really great day.